This is a tutorial on arithmetic sequences. To introduce what an arithmetic sequence is, let's first complete this example. Bob sells his first ticket at 1 o'clock and then sells 5 more tickets every hour. How many tickets would he have sold by 6 o'clock? How about by 7 o'clock? Well, at 1 o'clock, Bob has sold 1 ticket. And if he sells 5 more tickets, by 2 o'clock, he sold 6 tickets. Then if he sells 5 more tickets, then by 3 o'clock, he's got 11 tickets. And then he sells 5 more, so now he's up to 16 tickets. 5 more again, 21. And then 5 more again, is 26. And then by 7 o'clock, he sells 5 more, so it's 31 tickets. So by 6 o'clock, he sold 26 tickets, and by 7 o'clock, he sold 31 tickets. Now what if we didn't know that Bob sold 5 tickets every hour? What if we were just presented with the amount of tickets he sold? So first it was 1 ticket, then it was 6 tickets, 11, 16, 21, 26, and 31. These numbers are a sequence because they go in order. The order they're in is by the time that they were sold by. So 1, 2, 3, 4, 5, 6, and 7 o'clock. Could you look at this sequence of numbers and see that 1 plus 5 is 6. 6 plus 5 is 11. 11 plus 5 is 16. And so on, and so on. Because these are constantly added by the same number, these numbers are an arithmetic sequence. So let's look at a couple more sequences, and we'll see if they're also arithmetic sequences. So let's do this first one. 11 minus 3 is 8. So to get from 3 to 11, we would have to add 8. Now to go from 11 to 19, they would also add 8. And then 19 to 27 would also add 8. And then lastly, 27 to 35 would also add 8. So this sequence is an arithmetic sequence. Let's check the next one. To go from 1 to 10, we would have to add 9. But to go from 10 to 18, we would have to add 8. And then to go from 18 to 27, we would add 9 again. And then 27 to 32, we would only have to add 5. So since these numbers are all different, this is not an arithmetic sequence. So let's check our last one. 2, 1.2, 0.4, negative 0.4, and negative 1.2. Well, to go from 2 to 1.2, we would have to subtract 0.8. And then to go from 1.2 to 0.4, again we would subtract 0.8. And then from 0.4 to negative 0.4, again, would be 0.8. And then from negative 0.4 to negative 1.2, again, we would subtract 0.8. So this third sequence is an arithmetic sequence. Now there is an easier method to calculate arithmetic sequences instead of constantly trying to figure out what each number is consistently added or subtracted to. For instance, this sequence that we're given, 1, 4, 7, 10, 13, and 16, this is plus 3, plus 3, plus 3, plus 3, and added 3 one more time. But if we didn't want to go through the work to figure out how these numbers are changing, we could use this formula. This formula states that a to the n is equal to a1 plus n minus 1 times d. Now what does that mean? Well, our n is simply our position. N is our position. So the number 1 in our sequence is in position 1. The number 4 is in position 2. The number 7 is in position 3, and so on. A1 then is simply equal, in this instance, to 1. A2 would then be equal to 4. A3 would be equal to 7. A4 would be equal to 10. A5 would be equal to 13. And A6 would be equal to 16. So our AN is just our term, and the n is dependent upon what position the number is in the sequence. Now, the only thing we haven't explained now is this d. D is called our common difference. The common difference is what the sequence changes by each time. So in this instance, our common difference would be equal to 3. So let's see if we can apply this formula with a couple examples. Here in our first sequence, 1, 12, 23, 34, and 45. Here, 1 is our A1, and we don't know our common difference, but we do know the rest of our terms. So here's A2, and A3, and A4, and A5. What we're looking for, though, is A6 and A7. Well, to calculate this, we're going to use our formula. So it's a to the n is equal to A1 plus n minus 1 times d. Well, we don't know d. It's what we need to find. We know our A1. In this instance, it's 1. So we'll use one of these other terms to calculate our d. I like to use A2, but it doesn't matter which number you use. And we'll plug A2 in for AN. So what we'll use is we'll say that A2 is equal to A1 plus 2, because it's our second position, or it's A2, minus 1 times D. So A2 is equal to 12, so we get 12 is equal to A1, which is 1, plus 2 minus 1 times D. So we'll subtract the 1 from both sides. We'll get 11 is equal to 2 minus 1 is 1, so it's 1D, which means our D in this case is 11. So does that make sense? Do these numbers keep going up by 11? Well, 1 plus 11 is 12. 12 plus 11 is 23. 23 plus 11 is 34. And plus 11 again is 45. So it seems to work. So now we just need to solve for our next two terms, A6 and A7. So to do that, we're going to use the formula again. And instead of AN, we're going to solve for A6. A6 is equal to our first term, A1, which is a 1, plus, now our n is now equal to 6 because we're discussing the sixth term. So it would be 6 minus 1. And then our common difference, which you already found, is 11. So this would come out to be A6 is equal to 1 plus 55, because this is a 5, and then 5 times 11 is 55. So our A6 is equal to 56. So let's now do A7. We're going to do it the same way. We're going to use the same formula. So we're going to have A7 is equal to 1, because that's what our first term is equal to, plus 7, because our n is now 7, because we're looking for our 7th term, minus 1, and again our common difference is still 11. So this would be 1 plus 6 times 11, so A7 is equal to 67. So let's do our next problem. Our sequence starts with a negative 0.4, then goes to negative 0.1, then to 0.2, 0.5, and 0.8. So again, our first term is equal to negative 0.4, and we don't know our common difference. So again, we're going to use the formula. A to the n is equal to A1 plus n minus 1 times d. So we know our A1, and we know our A2, A3, and A4, and A5. But we don't know our common difference, so it's the next thing we're going to solve for. Again, you can use any of the terms you know, A2 through 5. I like to use A2. So we're going to solve for A2 is equal to A1 plus n minus 1 times d. So we'll plug in what we know. A2 is negative 0.1, which is equal to negative 0.4, because that's our first term, plus 2 minus 1, because 2 is n, because we're talking about our second term on the outside of the equal sign here, times d. So if we add 0.4 to both sides, we'll get 0.3 is equal to d. So our common difference is 0.3. So let's double check it real quick. If we add 0.3 to negative 0.4, we do get negative 0.1, and again does equal 0.2, 0.5, and 0.8. So that does seem to work. Our common difference is 0.3. So let's again solve for A6 and A7. So our A6 is equal to our first term, which is negative 0.4, plus, now our n is 6, because we're talking about our sixth term. Subtract the 1 and multiply it by our common difference, which is 0.3. So it's a negative 0.4 plus 5 times 0.3. Well, 5 times 0.3 is 1.5 plus a negative 0.4. So our sixth term, or A6, is equal to 1.1. So now let's do A7. Again, negative 0.4, because that's our first term, plus 7, because we're talking about our seventh term, minus 1, times our common difference, which is 0.3. This is D, this is N, this is A1. Again, solve this out. So this would be 6 times 0.3 plus a negative 0.4. This would go to 1.8 plus a negative 0.4. So our seventh term, or A7, would be equal to 1.4. Now let's look at our last example problem. It looks a little bit more intimidating because there are variables x in it, but we're going to follow the same steps and we'll find out that it really won't be any more difficult. So again, our formula is a to the n, which is equal to a1 plus n minus 1 times d. Now our first term, a1, is equal to 4. And we need to find our common difference. So as usual, I'm going to use our second term, and we're going to plug that in for an or a2. So it's 5 plus x, which is equal to 4 plus, now our n is 2 because this is our second term, times d, which we don't know. This is what we're solving for. So subtract the 4 from both sides, and you'll get 1 plus x is equal to d. So our common difference is 1 plus x. Does that make sense? If we add 1 plus x to 4, we do get 5 plus x. If we add 1 plus x to 5 plus x, we'll get 6 plus 2x, and then again 7 plus 3x. So this does work. So here we have a1, we also have a2, a3, and a4. So we need to solve for a5 and a6. Now a5, again we're going to use the formula. a1, or our first term, is 4. And then we're going to add it to, our n is 5 because we're looking for our fifth term. Subtract the 1, and then our common difference is 1 plus x. So let's simplify this. This is 4 plus 4 times 1 plus x. So carry the 4 in, and you'll get 4 plus 4 plus 4x. So our fifth term, or a5, is equal to 8 plus 4x. Alright, let's now solve for our sixth term, or a6. Again, we're going to use the formula. And our first term, a1, is equal to 4 plus, our n is 6, this is our sixth term, and then our common difference is 1 plus x. So this is 4 plus 5 times 1 plus x. Carry the 5 in, so you'll get 4 plus 5 plus 5x. So our sixth term is equal to 9 plus 5x. Now we have two more examples to do. The first one says, find the 103rd term of the arithmetic sequence if our first term, a1, is equal to 1 and our common difference is equal to 4. Now you could add 4 to 1 102 times, but that would take a really long time. So let's use our formula. A to the n is equal to a1, or our first term, plus n minus 1 times our common difference. Now they gave us our common difference. D is equal to 4. And our first term is equal to 1. And we're asked to find our 103rd term. So what we're looking for is A 103. Well, A 103, or our 103rd term, is just equal to 1 plus, now our n is 103 because it's our 103rd term, minus 1 times 4. You end up with 1 plus 102 times 4, which is 408 plus 1. So the 103rd term is equal to 409. we have one more problem to do. It's a word problem, and it's a little tricky. If Bill's change jar has $2.14 in it, and he puts $1.06 in it every day, how much money will he have for 48 days? Now what's tricky about this problem is it's tempting to use A1 as $2.14. And you can do that, but you have to realize that before day one happens, because he still put $1.06 in the jar on day one, this is really day 0. So day 1, or A1, would be equal to $2.14 plus $1.06. So A1 would be equal to $3.20. Now to figure out how much money he's going to have after 48 days, well, we know A1 is $3.20. The $1.06 he puts in it every day is how much the jar is going to change every day. So it's our common difference. So we'll use the formula. A to the n is equal to A1 plus n minus 1 times d. And our A to n is A48. Our A1 is $3.20 plus 48 minus 1 times 106. This becomes a 47, so 47 times 106 plus $3.20. 47 times 106 is $49.82. And then you have to add the 320. So our final answer, or after 48 days of putting $1.06 in, we end up with $53.02. And that completes the tutorial on arithmetic sequences.